So yeah, as the title says, I'm here to talk about communicating the impact of youth voter registration using Clojure and R. And before I get started, I just want to thank the clojureD organizers for having me out here. It means a lot. I'm really excited. So here's just a roadmap of the talk. I'm going to speak about a problem, which is that young Americans aren't engaged in their democratic process, meaning they don't vote. Maybe there's a solution to that, which is motivating participation by communicating their power to change the outcome of an election. And to build my solution, I'm using Clojure and R. And I think it's fun and maybe can also make good progress in the Clojure data science community's story and also politically. And I have kind of a case study in why rigorous data science is hard and how Clojure might help us. And maybe some ideas about future work, dream of simpler data science, and how to implement a tool to improve democracy. So this is a big problem. Americans don't vote. You could see all these other countries, and it's great how much all these other countries vote, or how engaged these citizens are, and the US is not. And especially young Americans don't vote. You see the bottom line is blue. That's people ages 18 to 29. You can see how much lower that is than every other age demographic. And just a note about why it's spiky, Americans turn out in greater numbers every 4 years when there's the general presidential elections, and then every 2 years there's congressional elections, and no one cares about that apparently. So I got inspired to think about this idea looking at this visualization from The Economist, which is what if everybody voted. You can see in the upper left the electoral vote count, if everyone, the actual result in 2016, and then at the bottom, a simulation based on polls if everyone actually voted. And you can see the outcome is quite different. Just a note about what these electoral votes mean. Every state has a certain amount of points that it counts towards the general election, and those points are based on the population size, roughly, of that state. And it's for almost every state, it's winner take all. So here's what if only young people's votes counted. You see on the left, that's only young people, and the actual results on the right, and they're quite different. And actually, in small print, in the actual results, you can see the number of points that each state in the US gets. So this kind of suggests that young people could make a huge difference. They don't turn out, and when they do, they vote in a very strong way. They vote strongly for Democrats. So maybe if a lot of them turned out, it would make a huge difference. These visualizations are great, and they got me thinking about this idea, but they're kind of limited in that they don't show how we are making progress. They don't show progress in action. They only communicate that maybe we could. And it shows voting, which happens all at once on election day. But we want to show that we're making progress kind of in real time so that we can get motivated, excited, like what are we working towards, and see that we're kind of getting there. So let's show registration. Let's visualize registration, which you have to do in order to vote, and many people aren't even registered, so they can't even vote. So just registering people is a huge step towards progress, and people who are registered are much more likely to vote. Not just because they can, but people who are newly registered are more likely, especially young people. So how do young people actually visualize progress? And it's not just young people, but especially people who are very familiar with technology, which young people happen to be. And how do people think about progress in a technological way? We think about loading bars, right? So we're downloading something. We're almost there, right? We're making progress towards having our file, whatever. So let's visualize progress as a loading bar. And this loading bar shows how how many people are currently registered to vote in a specific state, and then we have an estimate of how many people would have to be registered in order for young people alone to tip the vote, tip the result of the election. And so our task is to estimate this number, this goal number, which is quite difficult to do rigorously. You can kind of lie about it, but I don't want to do that. I want this to be kind of convincing, so people can really get excited and feel like, this is something we can achieve. Just a note why I'm doing it state by state. Some states, as you saw before, are worth many more points than others. So Texas is a good state to work on because it's worth a lot of points. And also it's a state that hasn't ever voted Democrat in recent history. So it's kind of hard for people to imagine it could. And this just shows a pathway towards that. So I'm a software engineer. And so thinking about this problem, I start thinking about architecture. And I basically know, okay, we have some kind of statistical model, it's a prediction. We have like a server that's gonna host the model, run the model in some way, and it's going to serve a website with this visualization, the progress bar. And hopefully, as a side effect, people get motivated to register and vote. So you already know we're at a Clojure conference. What am I going to use for the server and the progress bar, the website? I'm going to use Clojure and Clojurrescript because it's the best tool for web development. It's my favorite tool. I probably don't need to sell you guys on that, so don't have to spend a lot of time on this slide, but Clojure and Clojurrescript is great for web development and, of course, general programming. And when I'm using Clojure, I get to use all of these great libraries for the server and the client. I have access to the whole Java ecosystem and the JavaScript ecosystem, and that's awesome. So what am I going to use to build the statistical model? I'm going to use R. R is a great language for statistical programming. And why would I use R? It has this great ecosystem, has some similarities with the reasons why I like Clojure: pragmatism, some declarative and functional programming. It's got decent interactive programming. But the really important reason is that my advisor, who's helping me with the statistics at my school, uses it. That's how he likes to think, is in R. So I'm going to use R, and the most important parts about R, or some of the biggest selling points, right, are these great libraries. You see, like, I have Tidy Census, which is an API for accessing US Census and demographics information. I have some libraries for linear modeling, for imputation, and for graphics and plotting. And those are a big win if I can use them. I don't have to reinvent the wheel, saves me a lot of time, keeps me going. But the value proposition of doing most of the work in R is maybe not so strong. Like, most of data science work, some people say 80%, is just kind of mangling data from one shape to another. That's like the bulk of the work. And we want a really nice, flexible way to do that. And Clojure kind of provides this really great way to reshape data and model data functionally. We have these functional data structures that are heterogeneous and flexible. And thinking in data is a great programming experience and yields very robust and flexible programs. So maybe there's a way that we can use R from Clojure, use these R libraries the same way that I use Java and JavaScript libraries. So how are we going to do that? We're going to use Clojuress, which is a great new library for R interop, and allows me to do what I just said, call R libraries as if they were Java libraries, sort of mix and match code when I need. And for the data munging, whatever, I'm going to use a combination of TechML dataset and tech data type. But the real star of the show is actually just plain Clojure data structures. They are awesome. They're great for modeling the transformation of data in some shapes to another flexibly. So being able to use that is a big win for just regular data science. So we still have this task of how to actually predict electoral politics in America. And there's basically 4 really important demographic factors in America for predicting the results of elections and sort of people's political opinions. And that's race, age, sex, and education, not in a particular order. So we're going to need access to this kind of information and specifically the interaction between these things in many cases. And the other piece is that it's highly geographical, so you need to know where people are to make inferences about how they're going to behave. And we need this information at the county, which is like a district, administrative district of a state, at the county level, because that's sort of the level of granularity that is most meaningful. And that's also the smallest level that we can usually get data at. So here's a very high-level overview of how the statistical model works. Try not to get too into the weeds on this, but basically we start with some characteristics about each county. So that could be something like how urban it is versus rural. Could be something about the population size. It could be how white it is, how black it is, what are the racial demographics. It could be any number of things that are sort of indicative of what the county is like and maybe what the people are like in the county. And we want to associate or combine this data and make an inference about the connection with survey microdata. So that means people go around and they go door to door or somehow on the phone, and they ask people, what are your political opinions? What are your demographics? What's your demographic profile? And maybe some other opinions or some economic information. But just get a sense of what are the people like in different places. So we use information about what counties are like at the whole level or the aggregate level, and we kind of combine that with information about what people are like in that county. Specifically, you can get information, aggregate information about demographics at the county level, but you can't get too much detailed opinion information. That's microdata. So when we combine that, we can build these predictions about how different demographic profiles, so some combination of these 4 factors and where they are likely to register, vote, and which party they will support. And given those predictions, we can multiply that, roughly, by the population estimates for each county by demographic profile. So we have some estimate of how many people fit this profile, and then we're multiplying that by the rate at which that kind of person is likely to register, vote, and then what party they'll support. And from that, we can build some prediction of the election results. Let's break the predictions about demographics down a little bit more. We need these 3 pieces of information to kind of feed into each other. The likelihood to be registered has to feed into the likelihood to vote, because you have to be registered to vote. And then that has to feed into which party you're likely to vote for. And our task is basically to find out how high does the likelihood to be registered for a specific demographic, in this case young people, how high does that need to be to raise the level as a whole through this process. So if so many more people are registered, and then the likelihood to vote roughly stays the same, and then the likelihood to vote for a party roughly stays the same, then in aggregate the outcome will be really high. So we can't necessarily say we can't change the likelihood to vote as an independent variable. That's not what we're doing. We're trying to see how many people have to be registered, how many young people have to be registered specifically in order to change this election, moving through these probabilities, change the outcome. So doing this is pretty hard. We're looking at a picture right now of different counties and how I predicted them to vote versus how they actually voted. So each dot is one county in Texas, and the size of the dot is the population size of the county. And you really need to be going back and forth between visualization and code when you're doing this, because if you don't have some quality of information in your visualization, like in this case, the size of the county, you can't look at this and go, oh, we kind of predict the bigger ones wrong in this way, or we kind of predict the smallest ones wrong in this way. So you need that back and forth. So again, like access to these visualization libraries are super important. But kind of back to the challenges, you can see this graph right between actual and predicted. We want to predict what actually happened retroactively. And that's how we know our prediction model is pretty good. And so what that would look like if we did that is that all the points would be along this line. Actual would equal predicted. And you can see that's not the case. And part of the challenge of making these better predictions is combining incomplete data sets. So we get a lot of data sets, and they don't always have what we need. They have parts of what we need, and we're interested in some kind of aggregate inference about how the parts interact. So we really need a way to reshape different data structures fluidly so that we can put the parts together when we need to, and then take them apart and put them together in another way without having to write a ton of code and without having to redefine our data model or implement our data model at every level that we use it. We kind of want one place where we define our data model and then flexibly rearrange it. And this isn't just my problem. This is all data scientists' problem. So if we Clojuress can kind of crack that, that's a big win. I already mentioned most of the work data scientists do is data munging. So this is important. So I'll give an illustrative example of how we might want to combine data and how sort of it's normally done and how maybe we can do it differently. So we're looking at two tables here, two incomplete data sets or parts of information that we need to combine. And the first one is likelihood to vote Democrat by demographic profile. So in each county, we have a profile, which is a matrix of bits, and each row represents one combination of those bits representing every kind of demographic profile. So we have race, sex, and age, and you can imagine that there can be more here. And for each demographic profile, we've predicted elsewhere how likely they are to vote Democrat. And the other table we have is an estimated population count of each demographic profile. So we know in this county, this demographic combination is likely to have this many people. That's the population of people who fit this criteria. And if you remember this part where we multiply the predictions about how they're likely to register, vote, etc., by the population estimates, this is sort of roughly what we're doing. We have the estimates and we need to know, okay, if these people are likely to vote, then this is how many people will actually vote this way or that way when we multiply them. So this is just zoomed out the way that you might typically approach this in R, and this is not fun. You could look at this, and maybe it looks a little smelly to you. It's not dry, and you might imagine that it's not very flexible, and it's definitely not fun to write. let's take a closer look at that. So what we're doing is we're matching these cases of when we fit this profile, and we have a prediction about that, and then we're multiplying it by these columns with the estimate population for that profile. But you see here, like these, we can look at it in this view. These column names are just string concatenations of these domain entities. Like we don't actually want to think of them as strings, right? Where I've done race underscore sex underscore age. We want to think of them basically as a set, because we don't care about the order, and I don't want to have to remember it's race, sex, age. I almost messed it up just now, even looking at it. And also, sometimes we have different combinations in like sex, age, education, and what should be the ordering convention. And the data we're modeling, it's not a string, it's a set, and there's uniqueness, and the order doesn't matter. That's a set. So this is kind of showing what it looks like if you model it as a string versus if you model the column as a set. So we have these namespace qualified keywords, which I love. And we have, as the key, we have this tuple, which is a keyword estimate, so some information about what the column is like, and then a set of the entities that the column contains. And to build or reason about this kind of modeling in Clojure, this is kind of what we do. I don't want to go into too much detail, so I'm running out of time here. But just sort of looking left and right, you can see, yeah, the left side is very repetitive, but maybe it's clearer in some ways. Maybe it's more obvious from the get-go. Like looking at this, even as someone who writes Clojure, the right side, it's going to take me some time to think about it. And part of that is just my familiarity with this or that way of thinking. And part of it is also sort of our ability as Clojurers to do this kind of work, and it's very new. So we have some trade-offs to think about. We know this first one, simple versus easy. Maybe our Clojure one is simple, but it's not necessarily easier. And by that, it's definitely not familiar. And a lot of what I actually, what I have to do is to share my work with my advisor or just most data scientists who are used to thinking about tables in this way. And maybe the best way to manipulate tables in that sort of traditional way is by doing this process that's kind of repetitive and inflexible. So it's a work in progress to figure out the grammar that we want to express these data sets and the transformations on them. So just to wrap up, there's kind of one more thing to talk about in the architecture we haven't discussed yet, and that's the people get motivated to register and vote. That's what's the stack that runs on, right? It's Peopleware. It's community organizers, nonprofits, marketing experts, citizens, people who share this visualization, who get involved, register people to vote, talk to their friends, whatever. That's like how this kind of social change actually gets implemented. That's the stack it's computed on. So I have my work cut out for me collaborating with these kind of people, and it's important to keep in mind their use case and the problem that they're trying to solve, their view of the world, as much as it is the nitty-gritty of the data science and the programming. So it's important not to get too lost in that and focus on actually solving someone's problem, not just puzzles. And I do think that the Clojure data science-y approach could be a really great way to solve these problems more simply and directly. So there's a lot of promise there. Okay, that's it. Thank you so much.
Thank you, Nick.